Hello and welcome to our lesson on giant covalent structures and limitations of models. It's worth mentioning that there's a bit more information on giant covalent structures when we talk about allotropes of carbon in the next bit of the unit, but for now we're just going to do a general overview of their properties. Okay, so just to cover some key bits of information again, if you know that something has strong bonds, you have to assume it has a high melting point or a high boiling point, and a high boiling point, because strong bonds require a lot of energy to break them. And if you see or know that something has free electrons or free ions or delocalized electrons or ions, it means they can conduct electricity. And those are rules no matter what you're looking at. So sometimes exams come up with something you've never heard of before, but it tells you it has free electrons, and you have to make the connection, well, I'd never heard of this before, but it's got free electrons, so it must conduct electricity. So what type of bonding is this between a positive and a negative ion? Well, hopefully you would recognise this is ionic bonding. And what is holding these ions together? Well, this is electrostatic attraction. What type of bonding is this? The sharing pairs of electrons. This is a covalent bond. And what's holding the molecule together? Well, it's that sharing bond, that covalent bond. Strong bonds. What type of bonding is this? Well, this is a simple molecule, isn't it, with the strong covalent bonds and then the weak intermolecular forces. What's holding the molecules together? Well, the molecules are held together by covalent bonds, and the molecules are held next to each other by the intermolecular forces. So you've seen there are quite a few different models, and you need to know why we use different models and some of the advantages and some of the limitations of each of them. So these are the four that we generally use, and it's just worth pausing and making a note of each of these. So the two-dimensional models here that you would see. The advantage is it's a very simple diagram, and it shows the atoms, all the atoms in the molecule. It shows what they are and how they're connected to each other. The disadvantage is it doesn't show the size of the atoms, and it's not three-dimensional. Now, of course, molecules in real life are three-dimensional, so that is a definite limitation. Now, a 3D diagram is great because it shows the arrangement of the atoms and the structure, and it's three-dimensional. But it only shows the outside of the structure. I can't see internally if they're all the same, or if there's something else going on there, or maybe if it's even hollow. I can't see. The dot and cross diagrams we've been working hard on, well, the advantages of these are they show how the bonds are formed, and they show where those electrons are coming from and going to. The problem is it doesn't show the size of the atoms compared to each other, and it doesn't show the arrangement of the atoms in real life. Now, a ball and stick is something you might ball and stick model you might see in class. It's great for showing the three-dimensional shape. It's more realistic than maybe some of the other models. However, this gap here that we seem to have doesn't exist in real life, so it's a little bit of a misconception that there's a great big gap between these atoms. That's not true. And of course, it's not to scale. And so those are the limitations of the ball and stick model. It's worth remembering at least some of these. Okay, so what is this diagram showing? What type of bond is this showing? Well, hopefully you'd recognise that this is the giant ionic structure that we've previously talked about. And how is the giant ionic structure, or the giant ionic lattice, made? Well, it's made with many ions, charged particles. You can see here the minuses and the positives. Well, just like those ions, which made these giant ionic lattices, non-metals can also form giant structures with other non-metals. And these have got, unfortunately, two names. They're either called giant covalent structures, or they're sometimes called macromolecules. So we've got a few examples here. Silicon dioxide, which is what's making sand or glass, you can see here on the left, and it's just made of silicon, oxygen, just over and over and over again in this huge structure. And then these all here are what we call the allotropes of carbon. So all of these are actually made of carbon atoms, just put together in slightly different ways. And we're going to look more detail about why carbon in particular tends to form these giant structures. But giant covalent structures or macromolecules have similar properties no matter what they're made out of. So our core concept, giant covalent structures or macromolecules are made of many atoms bonded together covalently. So we'll talk about non-metals. Now they have, obviously it's a covalent bond. There's none of those weak intermolecular forces there. So strong bonds, so they're going to have a high melting point and a high boiling point. And there's no free electrons in these structures, and so they do not conduct electricity. Like I say, we're going to go on to this in a bit more detail in the next part of the unit, but that's it for now, and I'll speak to you later.